Hey guys, welcome back to chapter 4. We are going to take a path into all things covalent bonding. So in the first half of the chapter, we got introduced to ionic versus covalent. Ionic was when electrons are transferred, we get charged particles, positives attracted to negative. For covalent, we've got a nonmetal bound to a nonmetal. And here electrons are going to be shared. So the second half of this chapter is going to be getting to know covalent bonds. How do we depict them? How do we represent them? And then just getting to know what it means for electrons to be shared. So first things first, for covalent bonds, we will use something called Lewis structures to depict these covalent bonds, to depict this sharing. You've had a little introduction to the Lewis structures when I did the story about magnesium and chlorine, and I used dots to represent electrons. Well, that's exactly what the Lewis structure is. It's when we focus on the valence electrons, of course, those are the only electrons that are available for bonding, and we depict those valence electrons as dots. So let's take a look at an example. Let's take a look at the element oxygen. Okay. So looking at the periodic table, we see that oxygen is in group 16 or 6A. It has 6 valence electrons. So we're going to write those valence electrons around the oxygen atom. What I like to think is there's an imaginary box around each of these atoms. And on each side of that imaginary box, it can hold up to 2 electrons. So if I were to do the 6 valence electrons for oxygen, I would say 1, 2, oh goodness, let me get ones that stay, there you go, 2, 3, 4, 5, 6, wait, 2, 4, 6, done. All right, so here's the Lewis structure for oxygen. It's got 6 valence electrons. We depict those valence electrons as dots, and we put dots up to 2 on each side of that imaginary box. So that's going to be how we depict Lewis structures. So here's just a representation, a little bit prettier than mine. So we have those 6 dots representing the Lewis structures. Okay. So Lewis symbols are used to show the bonding in the atom and the capacity that it has to bond. Dots are placed on 4 sides of the symbol, and it's placed on each side before they are paired. I'm not a big stickler on that one. It makes more sense to start pairing them when we start making compounds. But really just know that 2 dots on each side until we run out of valence. So the other thing we're going to talk about with covalent bonding, it's very similar to what we talked about in ionic bonding. For covalent bonding, remember that the whole purpose of the exercise is to obtain a stable electron configuration. We know our noble gases have stable electron configurations. And what makes them particularly stable is the fact that they have 8 valence electrons. So 8 is kind of a magical number for us as chemists. So here we see the electron configuration for neon. We see that the valence electrons are in that second energy level. And most importantly, we see that there are 8 electrons in that energy level. If I were to write the Lewis structure for neon, I would write the chemical symbol, and then I would draw 8 electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So that's the Lewis structure for neon. So this idea of having 8 electrons is so important that it's given its own kind of name or term. The term we use is an octet. So an octet is having 8 electrons in the valence shell. and those 8 electrons are particularly stable. So the whole purpose of the bonding exercise, whether we transfer or we share, we're going to do that so that we are touching 8 electrons. Now, as always, there are exceptions to the rule. So there is one exception that I need to tell you guys about. So if you guys look at your periodic table, you'll see that helium is added to the very top of the noble gases. Helium does not have 8 valence electrons. How many electrons does helium have total? He's the second element. He's got 2 electrons. But as it turns out, those 2 electrons make the first energy level full. So it is stable, but it is an exception to the rule. So helium has what we call a duet. That's having the 2 electrons in the valence shell. So helium's important because there's kind of a handful of atoms that want to be like helium. So they'll be okay with a duet. So here's some examples of atoms that are okay with a duet. The main one for us, the one that you guys will need to know, is hydrogen. So as we are drawing these Lewis structures, hydrogen will be okay and will only want to touch 2 electrons. All right, so purpose of the exercise, we want to touch 8 electrons unless we are hydrogen, then we only want to touch 2. What I'm going to go over now is an example of a Lewis structure for a covalent bond. I have slides that have these steps kind of laid out, but for this one I might just kind of sit back and watch. So the Lewis structure that we're going to do is kind of the poster child for covalent compounds. We're going to do water, H2O. Okay. So step number 1 is to calculate the total number of valence electrons. So the way we're going to do this is we're going to take and we're going to decide how many valence electrons each of these atoms brings to the party. So hydrogen's in the first energy level. He's going to bring 1 valence electron. Hydrogen still in the first group, 1 valence electron. And oxygen is in group 16 or 6A. He's going to bring 6. So when I add these all together, I have 8 valence electrons at my disposal or to use in my Lewis structure. Step number 2 is to put the elements on the paper in the kind of skeletal structure, the way I think they're going to be arranged. So arrange. Okay. So a couple helpful hints here. Think symmetrical. So here we've got 1 oxygen, we've got 2 hydrogens. So very likely oxygen will be in the middle and we'll see a hydrogen on either side. Okay, that's a pretty good place to start. The other thing to consider is hydrogen. So hydrogen will always be on the outside. So for example, it would not make sense. Oops. It doesn't even make sense. I can't even draw it. It would not make sense to write something like this because we'll never find hydrogen in the middle. It will always be on the end, or what we call terminal. Okay, step number 3 is we're going to distribute electrons to fill octets, or in this case, duets. Okay. So I always like to put electrons on the paper that are being shared between two elements. So these two electrons are being touched or shared between oxygen and hydrogen. So that was what a covalent bond is sharing electrons. So on this other side, I'm going to put these two electrons here and here. Okay, so these electrons are being shared. I've got 8 valence electrons that I need to put onto the paper. Right now, I have 1, 2, 3, 4 on the paper. So after I do the electrons that are shared, then I need to distribute the rest of them so that everybody has an octet or as many octets as I can. I'm not going to give any more to hydrogen because he's okay with 2, but oxygen does need more. So I'm going to give him 4, 5, 6, 7, 8. So I'm stopping because I ran out of electrons. I had 8 electrons that I had to put into my picture, and I have 8 electrons in my picture. So now I just want to go back and make sure that everybody is touching the number of electrons that they want to touch. So this hydrogen right here is touching 1, 2 electrons. Remember, hydrogen's okay with duet, so he's happy. This hydrogen over here is touching 1, 2 electrons. He is also happy. And then this oxygen in the middle wants to touch 8. He would like to have an octet. So he's touching 1, 2, 3, 4, 5, 6, 7, 8. So he is happy. Yes, I draw smiley faces on my atoms. It's fine. Okay. So this is the Lewis structure for water. We used all of the valence electrons that were brought to the party. We made sure that everybody's octet or duet was filled, and this is how the electrons are arranged for this particular molecule. So looking at our Lewis structure for water, I'm just going to redraw it here. One of the things that you'll notice is when we draw electrons into the picture, we draw them in pairs, right? We draw 2 dots at a time. Well, there's 2 different types of electron pairs, just some terminology that we want to talk about here. So a bonding pair is going to be electrons that are shared between 2 atoms. So for example, looking at our water, these guys right here would be a bonding pair because both the oxygen and the hydrogen are touching them. They're being shared. We have another example of a bonding pair right here. The other pair that we see is something called a lone pair. So a lone pair belongs to just one individual atom. So here, oxygen, we see these 2 electrons that are sitting on the top. Nobody else is touching those electrons, just oxygen owns them. So that would be a non-bonding, belongs to just one. I see another lone pair down here on the bottom. So looking at this water molecule, I see 2 bonding pairs, and I see 2 lone pairs. The last thing I want to talk about with this example is just a slightly different way to symbolically represent this. At some point, you are going to get sick of drawing dots. So sometimes bonding pairs, instead of drawing them as 2 electrons, sometimes we'll draw a bonding pair as a straight line. Okay? So just a different way to represent it. But just remember that this straight line means that there are 2 electrons that are being shared. So as I'm counting electrons, I would count 1, 2, 3, 4, 5, 6, 7, 8. So each line is worth 2 electrons. So here's just kind of a way that we represent that in digital format instead of my handwriting. So to conclude this video, here's what I said about the list of steps that I kind of talked you through. So step number 1 is to determine the total number of valence electrons. I don't like to think about like, oh, that one has 6 electrons, so it's going to make 2 bonds. It works for a while, but then sometimes it starts to break down. So I find it easier if students just say, all of these atoms collectively brought 8 valence electrons or 14 valence electrons. It's just easier to talk about the collective. Step number 2 is arrange the symbols to show how the atoms are bonded together. So the 2 helpful hints I talked about here are number 1, try a symmetrical approach. And then number 2, hydrogens will always be terminal. They'll always be on the outside. Step number 3, distribute electrons, completing octets of the atoms bonded to the central, and then by adding lone pairs. So as we get to more complex molecules, you'll see this in action. But I start with the bonding pairs. Then I would fill octets of the terminal atoms, and then I would end on the central atom. And then step number 4 is very important. Compare the number of valence electrons in the Lewis structure to the number determined in step 1. That'll be important. Mistakes happen. Sometimes you lose track of the dots. So taking a second to go back and just make sure that you have the same number of electrons that you're supposed to have is very important. And then number 5, we'll get to this at a later time, but confirm that there's an octet on the central atom. If there is not, then we'll explore double and triple bonds. But for right now, we're just going to pause that one and come back to that. Okay. All right, so that was your introduction to Lewis structures. The next video, I'll work through a couple examples. And then we'll go into that creating multiple bonds. That'll be the next topic. I hope you guys found this helpful.